Okay, good morning and welcome everyone. It's a pleasure to have all these experts here. We're going to discuss M theory and mathematics. We have a very rich program all the way from structural aspects of M theory down to compactifications and dualities and branes and structure of field theories, supersymmetry, quantum field theory. And I look forward to all of that. But before we get there, we're going to have a word from our dean, Marta Losada, who's also a professor of physics here at NYUAD, working in a close-by area, which is phenomenology and experimental high-energy physics. So, Marta, would you like to give a word?
Well, good morning, everyone. I really am here just to give you a very warm welcome to NYUAD. I don't know how many of you have had the chance to be here before in the region. If you have never been here, your first time, I'm sure you're being really fascinated by this place. I arrived as dean here just a few months ago, so I am still really enjoying all of the new experiences of what I find here at NYUAD, but also in the UAE. I think it's really full of potential in so many different ways, both at the institutional level, in the division of science, and of course for the country, and their perspectives and the growth they want to have, and the funding that they're putting in place for research and research in science. I know that you really don't want to listen to me, that you're here to discuss amongst yourselves, to listen to, all of your presentations. I hope it's really enjoyable. I'm sure it is. I've checked the program. Just a small, a short anecdote. I used to sit in the String Palace, for those of you that are old enough to know what that is or was, so many years ago. So I had the great opportunity of listening to many, many seminars and conversations on these topics. I wish I could stay. Unfortunately, I cannot. I have to go right over. We have a new faculty joining, and we have a whole process of onboarding and integration with that new faculty. But I hope you really have a wonderful workshop. I couldn't miss coming back to say hi to everyone, given Hisham's invitation. So I'm really pleased to be here. But I really, really hope that it's extremely successful and that you really enjoy and will come back again to NYUAD. So thank you very much.
Thank you so much, Dean. Thank you so much. Thank you. Okay, so this is going to be recorded. I hope it's okay with everyone, speakers and attendees. There's a bit of a technology agreement here. So when we have questions and answers, whoever is going to ask a question should hit a button with a mouth picture on it, and then speak up. It might take a little bit of time to get used to it, but you could try that. And then when you're done, hit it again, and the red light will go off. But we'll coordinate accordingly. So we'll, next, what we're going to have, Mike Duff was supposed to be here to give us a lecture. Unfortunately, his health did not allow him to be here. So one option that we suggested is to have a live video conferencing. That did not work for various reasons. But then Mike was kind enough to have a pre-recorded interview that we had with him, Urs and I, the other day. So we're going to show that. So it's inevitably non-technical. It's going to be a perspective that he had, having lived through the early days of pre-M theory and M theory development. So we'll hear a video on that in a few minutes. So it's a pleasure to have Mike Duff, to interview Mike Duff on the subject of M theory and M brains. This is part of interview and a contribution from Mike to the workshop M Theory and Mathematics 2020 at New York University, Abu Dhabi. You had co-discovered early in 1980s some core ingredients of M theory, like membranes. Um, and then later on, in 1995, this came to be known as M theory. How do you reflect on that?
Well, reflecting on M theory is quite a big challenge. The story of M theory began with the story of 11 dimensions. And it was 1978, I think, when Werner Naum pointed out that supersymmetry places an upper limit on the dimension of space-time, which was 11. And so in the early 80s, my colleagues and I looked to 11-dimensional supergravity as a candidate for a unified theory of the fundamental forces. And that involved compactifying the 11 dimensions down to 4. But that had its problems. The theories we looked at were not phenomenologically very promising. And whether you have extra dimensions or supersymmetry, the problem still remained that Einstein's gravity was incompatible with quantum mechanics in the sense that the theories were non-normalizable in the sense of conventional quantum field theories. So when string theory came along in the 1984 string revolution, 11 dimensions got pushed to the sidelines, and we were told that 11 dimensions was barking up the wrong tree. But some of us thought even then that there's something not quite right. Why do superstrings live in 10 space-time dimensions if supersymmetry allows 11? And the next major contribution was when Bergsoft, Sezgin, and Townsend discovered the 11-dimensional supermembrane. And for me, that was the starting point of what I would call M theory, because it said, fine, strings are fundamental and live in 10 dimensions, but you have these membranes which seem equally fundamental, living in 11 dimensions. And my colleagues and I, Stell, Howe, Inami, were able to show if you wrap this 11-dimensional membrane around a circle, it looks like a 10-dimensional string. In fact, it looks like the type 2A string. So for us, that was proof, if proof were needed, that membranes in 11 dimensions were part of the big picture, including strings. However, that view was not a popular one, I have to say. The overriding view at that time was that space-time had 10 dimensions. It was occupied by strings, which are the theory of everything. And all these other objects, these brains, were theories of nothing. That was the conventional view. So in the early 90s, there were sort of two communities, if you like. The string people were doing their thing in 10 dimensions. The membrane people were doing theirs in 11. And it wasn't clear if we were on the same page or what. And then, as you know, Edward Witten made this startling speech at the University of Southern California, where he pointed out that the 5 consistent string theories and 11-dimensional supergravity were not, as we previously thought, 6 rival theories of everything. They were 6 different corners of the deeper, more profound theory that he called M theory. Now, given that we've been arguing in favor of membranes, the fact that the theory got called M was something of a Pyrrhic victory. I mean, it was saying, well, maybe membranes, but we're not completely sure. But for me, anyway, it was clear, I think, that branes were just as important as strings. And Joseph Conlon, writing in a recent book on string theory, says that when he saw the paper about wrapping the brain around the 11th dimension in the in the late 80s, he was shocked because the theory of the history that he'd been brought up with would not have allowed such a thing until 1995. So M-theory had a strange history. I could summarize my research in the 1980s as arguing for space-time dimensions greater than 4 in the early 80s and world volume dimensions greater than 2 in the late 80s. And that struggle was by far the harder of the two.
Yeah, that's very interesting. So similarly in the late 80s also, the regularized quantization of the supermembrane led to the matrix model, which later on was rediscovered as D0 brane quantum mechanics, and then hailed as a also contender for a definition of M-theory. Also, how do you reflect on this curious M-theory conceivement?
Well, it was quite usual for discoveries that were made in the 80s to reappear in the 90s. I don't want to diminish the importance of the matrix model. It was very important. And they built on the earlier work of the point-blank, what we would now call D0 brains of the late 80s. But matrix model itself was not all of M-theory. It was a corner of M-theory, and it told us certain interesting things. But there were interesting things about M-theory that it didn't tell us. So I think we're still looking, in fact, for what M-theory really is. We have a patchwork picture. We understand it in various corners, but the overarching big picture of M-theory is still waiting to be discovered, in my view.
So in your in a review, your famous review, M-theory, the theory formerly known as strings, in the concluding section, you wrote, the overriding problem in superunification in the coming years will be to take the mystery out of M-theory while keeping the magic and the membranes. What do you think is the status of this overriding problem today?
Well, it's still there, of course. M-theory in 1995 was very promising, and it's taught us a lot about the fundamental interactions. But the final theory is still not with us. And my view, and I've consistently held this view since I first started in quantum mechanics, is that we have to take a long-term stance. There'll be no overnight miracles. We have to keep beavering away, chipping away, and hopefully one day we'll find the answers. So I'm optimistic that there is an M-theory without the mystery, but I wouldn't like to put a time scale on how long it's going to take us to find it. So my argument would be for patience is what we need right now.
That's good.
Of course, that's not popular with the journalists and critics who want instant gratification, but I think it's, if we look at the discoveries that have had the greatest impact recently, the Higgs boson took 50 years between its prediction and its discovery. The cosmological constant, if indeed that's what dark energy is, would be 100 years between the prediction and the discovery. Similarly, gravitational waves. So there's no reason to think that a theory of everything is going to come along any quicker than these other discoveries. And so we just have to keep hoping for the best.
Yes, that makes sense, definitely. So in the late 90s, you wrote in Scientific American and also in your book on M-theory future historians may judge the late 20th century as a time when theorists were like children playing on the seashore, diverting themselves with the smoother pebbles or prettier shells of superstrings, while the great ocean of M-theory lay undiscovered before them. How do you look at this prediction 20 years into the 21st century?
Well, I hope you recognize that most of those words were of Isaac Newton. I just made a few substitutions in the right places. I still hold the view that perturbative 10-dimensional strings, as they were pursued in the late 80s, will be seen to be a small corner of the final theory. That's not a view that's necessarily shared by others. Ed Witten, in fact, wrote to me after I wrote that to argue that he didn't share that view. But there's a certain faction that believes that strings are more fundamental than brains because string theory admits a perturbation expansion. But in my view, that's not the criterion for what's fundamental and what isn't. God does not do perturbation theory. Perturbation theory is what we do because we don't know any better. So the fact that brains do not admit a perturbative treatment and strings do is not, in my view, a reason for thinking that brains are less fundamental than strings, especially since strings are just a limiting case, as we've seen, of brains. I don't see how you can maintain that one object which is not fundamental has a limiting case which is. So we have to treat them democratically.
Okay, so in your interview by Farmillo last year, you said, the problem we face is that we have a patchwork understanding of M-theory, like a quilt. We understand this corner and that corner, but what's lacking is the overarching big picture. So directly or indirectly, my research hopes to explain what M-theory really is. We don't know what it is. Do you have a hunch what the form of the answer might eventually take?
No, actually, I don't know. I wouldn't like to predict what the ultimate picture of M-theory will be. I imagine it will be something quite different from what we can imagine now. Going back to how the M-theory has developed, one curious feature of the big story is the ADS-CFT correspondence. Because when Maldacena wrote his paper, he had three examples: ADS4 cross S7, ADS5 cross S5, ADS7 cross S4. Two of those were 11-dimensional M-theory vacua, and the other one was type 2b. But if you look at the papers that have been written since Maldacena's seminal contribution, the vast majority of them have been on the ADS5 cross S5 story. It hasn't, for whatever reason, there hasn't been the same progress in M-theory as a result of that. So the ADS-CFT correspondence, in a way, diverted attention away from the goal of finding a unified theory of all the fundamental forces starting from 11 dimensions. It's been tremendously successful in its own way. Maldacena's paper is the most highly cited paper in history, but it has not, strangely enough, contributed to how we unify the strong, weak, and electromagnetic forces with gravity. At least I don't think it has. That's a different problem. And I would have been happier, I think, looking back, if we were further down that road since 1995 as we are. But I'm still optimistic that we're on the right track.
So you believe we ought to get back to that original big question about what's the nature of M-theory?
That's my view, yes. But of course, in order to do that, you have to have some good ideas, and we need more good ideas.
That's fair. So in that same interview with Farmelo, you next said, in a certain sense, and this is not a popular statement, I think it's premature to be asking what are the empirical consequences, because it's not yet in a mature enough state where we can sensibly make falsifiable predictions. Would you like to expand on that?
Yes, well, it was harking back to the remarks I made a few minutes ago about the time lag between the germ of a theoretical idea and its ultimate empirical confirmation. Another good example would be quantum entanglement. The problem was spotted in the 1930s, Einstein, Rosen, Podolsky. But it wasn't until the 1960s that John Bell came up with a falsifiable prediction. And it was another 20 years before Alan Aspect did the experiment. So my view is that theories of everything are going to be similarly require a large time lag between the original idea and their confirmation. And that's why I think M-theory is not yet in a mature enough stage for us to make falsifiable predictions. We don't understand the theory sufficiently well yet to do so.
So should we try to focus on understanding it first, and then it will naturally give us predictions, perhaps? Is that a view?
That's what I would recommend. But of course, progress comes in directions that you often don't expect. So I don't want to predict that progress will come from a particular, sorry, my telephone's ringing, a particular direction.
I see. A similar point was made recently by Tom Banks in a critique of the 15-year-old discussion of about the non-perturbative nature of the theory and about the landscape of de Sitter vacua. Do you think it's possible that the actual formulation of M-theory will show that much of the putative landscape of string theory is not actually there? Going back to the comparison of M-theory and string theory.
Superficially, I would say no, because M-theory has even more vacua than string theory has. So the landscape problem is has not gone away. What's often not appreciated, though, I think, is that if we were to follow the critics of string theory and M-theory and stop doing them today and start tomorrow with a blank sheet of paper and a sharp pencil and say, where do we go from here? The landscape problem would still be there. The problem of why you pick one physical vacuum from an infinity of mathematically possible vacua is a problem that's going to be there whether you do string theory, M-theory, or not. So I'm agnostic about the multiverse. I don't know whether we live in one universe or many, but there again, we have to keep beavering away and hopefully the truth will out.
Yeah. So do you envision any role for mathematics if you are able to map M-theory to mathematics? Do you think mathematics has something to say?
It certainly does, because in the absence of empirical data, what do we have to guide us? We have consistency is our criterion. So whatever our theories are, they must be, first of all, mathematically consistent, with no self-contradictions. And they must be consistent with what we already know to be true. So this is, in a way, a straitjacket that constrains our speculations and our projections of where the theory is going to go. And it's a very severe straitjacket. We can't just dream up any old thing and expect it to be mathematically consistent or consistent with current knowledge. So mathematical consistency has a vital part to play. And as you and your colleagues are aware, sophisticated mathematics is becoming more and more important in understanding M theory. And it's going to require the kind of mathematical approaches that you were doing to sort it all out, I'm sure.
Thank you, that's good. Good to know. So finally, how do you envision the future of activity in M theory should look like?
Well, there again, I don't want to make any rash predictions. My view of research is a Darwinian one. You find the brightest people, you give them the money, you let them get on with it, and they will go wherever they will go. And I don't think one should try and engineer from above the directions that research should take. Let the imaginations, pick the best people, let their imaginations wander, and we'll see where it takes us.
And let it flow naturally. Right. Okay. Yeah. Any final words of
only
advice?
that I wish your conference every success. I'm delighted that you're focusing on M theory. I'm sorry I won't be there in person, but I'm confident that it will be a wonderful conference.
Thank you so much. We appreciate it. It has been a pleasure, Mike Duff. Thank you so much.
You're very welcome.
Thanks. Thank you.
But we appreciate Mike's input. It was very insightful. So Mike is not here to answer questions, but we could open the floor for any comments. I don't know if we have anyone who was around in the 80s, maybe Chris or Dimitri or Ashel. Any comments or remarks, reflections? Okay, so we got praise from Mike that this is a good endeavor what we're doing here.